Welcome to the 17th of Istanbul Commerce University Science and Society meetings. Today we have a special guest, especially from my point of view. It is a very special and honorable guest. And today we will talk about virtual network environments and open marketplace and service orchestrations in those environments. Before going into the subject, the topic, I would like you to introduce my guest, Professor George Rouskas. Is an alumni distinguished graduate professor and the director of graduate programs in the computer science department at North Carolina State University. And he is also an IEEE fellow. He received a degree in computer engineering from National Technical University of Athens and MS and PhD degrees in computer science from Georgia Tech. His research interests include network architectures and protocols, optical networks, network design and optimization, performance evaluation, and he is a recipient of NFS Carrier Award. He currently serves as the founding editor-in-chief of IEEE Networking Letters and the steering committee of the OFC conference. But besides all those information, he is also my PhD. He was my PhD advisor. So this is why it is a very special day for me to host him in this webinar. I wish we could have the chance to host him personally in Istanbul, in our university. But unfortunately, for this webinar, it will be virtually. But I hope in the next meetings, we will have him here in Istanbul and have the chance to talk face to face. Before going into the details of his speech, I will let him to give his speech, but just tell that virtualization is a very important topic for today's, especially this pandemic showed us that virtual environments became much more important. We know that digital transformation is a reality, but we were not expecting it to come so drastically in one day, unfortunately. But we were almost ready to this transformation, and we just increased the speed of this transformation in this last year, unlike the previous 5 years. But with this transformation, we have a lot of new opportunities and new research areas. And today, Professor Rouskas will show us an important topic, how we can organize and orchestrate virtual network environments. And I don't want to spend much more of your time. And here, it is your time, Rouskas. Welcome again.
Thank you, Halim. So good evening, everyone. I know the time difference there, it's late afternoon. I'm really glad to be part of this series for Ticaret University. As Halim said, he was my PhD student some time back. I'm not going to say how long because it will reveal our ages, right? But I can certainly say that if we had this pandemic at that time, we would definitely be lost. I mean, the one silver lining of the pandemic was that the technology was at a mature point that allowed us to, continue our activities virtual to the extent possible. So, I very much appreciate your invitation. I wish I had the chance to visit you at Istanbul over those years, but I'd certainly welcome the opportunity to stop by. So, let me share my screen and okay. So can you see? Okay, so this is the full screen now. So what I'm going to talk to you about is work that we have carried out as part of a NSF grant, and NSF stands for the National Science Foundation here in the US, about an open marketplace and service orchestration in virtual network environments. And um, yeah, so here's an outline of my talk. I'll just talk about network virtualization in general, and just to make sure that we are all on the same page. And then I'm going to get into three pieces of work that we have done. One is a marketplace for network services. I will try to provide you with um, the motivation for that. And then the algorithmic part, which has to do with how to orchestrate services in such a distributed environments. And this line of work has there's a special term for that, which is called service chain routing. And I'm going to talk about how to solve that particular problem. So I'm going to start, with some of the basic terminology. And so virtualization is just an abstraction of physical resources, right? That allows different users to see different views of those resources. And this is a concept that goes back a very long time, actually, to the beginning of computing, right? And so, when you take your first operating systems class, you learn about virtual memory. And then you also learn about virtual machines that virtualize the operating system platforms. There's virtual storage area networks, and then in the last 10 years or so, we have virtualized computing itself. So we have these virtual data centers, right? And so the natural next step, and this is something that has happened in the last 10 to 12 years, is to extend this concept to networking. So the idea then here is that you have a physical infrastructure, which is the one here at the bottom, and the physical infrastructure consists of these routers or switches and the links that interconnect them. And this infrastructure, using virtualization, can support different networks. So you may have, let's say, virtual network 1 here in blue, and then a virtual network 2 that have not only, they see not only a different topology, right? So you can see how the topology of virtual network 2 is different than that of virtual network 1, but much more than that, they may be running different protocols, algorithms, and so on. So virtual network 1 may be running one routing algorithm, and network 2 may be running a very different algorithm. If you look at the historical perspective of virtualization in networking, again, there's a long history for that. You probably are aware with virtual LANs. For instance, in Ethernet, you have colored ports where allows certain ports of the network to communicate with each other, form a broadcast clouds. There's a virtual service networks. Then you have virtual private networks where you have an organization that uses the public infrastructure to connect different sites that are located away from each other, and they need security and specialized routing algorithms. Back in the 90s, there was this concept of active and programmable networks that did not really come to fruition, and the reason for that is because it required switches and routers to execute code carried in the packets, and so for the carriers and the service providers, that was certainly a point that they did not really want to introduce. But after that, we've had, you may have heard a lot about overlay networks or peer-to-peer networks, where these are now virtualization at the application layer, okay? And so, you basically download an application and you connect with other nodes or people who run the same application. And so that is kind of a virtualized network. Now, the one particular aspect that I'm going to be addressing here is what is called network function virtualization, or NFV, okay? And if you look at historically what has happened is that any services that you wanted to introduce into the network was implemented in what was called middle boxes. And I give you an example here. Okay, so let's say you had network address translation, okay, to provide security. You had a NAT box that you put at the entrance of your network, and so all the traffic had to go there. If you wanted to do encryption, then you had an encryptor box that you put into the edge of the network, and you used it there. Firewall, deep packet inspection, load balancer, all these functions, when they were first introduced into the network, they were standalone boxes, okay, that performed this function only, and then this traffic, all the traffic had to go, that had to use that particular service, had to go through that particular device, okay. Now, and so in the last, about 10 years or so, it was recognized that this is, while this has worked well for, the last, 30 years or so, it is not the most efficient or scalable solution. And so people moved away from that, and now they implement these network functions as just software modules, okay? And rather than having specialized, specially built middle boxes that run this particular function, what they do is they consolidate these virtual network functions on general purpose servers, okay? And so your traffic still has to go through the server that performs that particular VNF, but that server can be anywhere in the network and can be called up at any point in time, okay? Just like you can do with software, but you cannot do with hardware. And so this is the idea here, is rather than having hardware implementing these services, VNF1, VNF2, VNF3, whenever you need some of these, you instantiate a server somewhere in the network that performs this particular function, and then your traffic has to basically follow a path that takes it to the servers where these transformations have to be performed, okay? Now, once you do that, right, there's a lot of benefits. So first of all, you have reduced costs because you migrate to software, okay? You can have elastic scale up and scale down. So if at some point you have a lot of traffic coming into your network that needs to have a certain function, then you can instantiate more servers to handle that, right? You can't bring middle boxes in real time and install them in the network. Faster time to deployment because you're dealing with software, not hardware. And then you have a lot of efficiency in space, power, cooling, and so on in your data center for doing that. So all these are the benefits, right? But there is another interesting thing that can happen as well, okay? And that is that if I go back to this picture down here, is that now I can introduce services that go beyond the ones that typically are implemented as middle boxes, okay? So it can be any service. So if you think about the internet today, okay, if you look at the applications around it, then you will see that there's a huge ecosystem of applications, okay, that build upon each other. And so this ecosystem has evolved tremendously over the last 20 years or so, okay? Whereas if you look at inside the network, right, the protocols that are operating today are pretty much the same as those that operated, back at the beginning of the internet. So another interesting thing then is that now you can introduce these services and you can potentially think about customizing the paths that you take. And the analogy I like to give here is the airline analogy, right? If you're gonna go from, in this particular case, if you're gonna go from Raleigh-Durham in North Carolina, where I live, to Athens, okay, to visit my family, then what I can do is I can go to an online planner like Travelocity or Expedia and so on, and I can put in the beginning and end of my journey, and then I have a couple of options on the left-hand side, as you can see here. How many stops, what airlines to include, and all that. And then the travel planner is going to take a few seconds, will come up with a bunch of options. And here I'm giving you one option, so that just the first page of these options that continue way down, okay? And I may not necessarily choose an option that takes me through Russia to go to Athens, okay? But if I scroll down or if I change my my criteria, I will get a plan or an itinerary that is to my liking. And so we would like to do the same thing for networking, and so for inside the network. So our first piece of work that's looked into that is creating a marketplace for network services. And the idea is here to give you choice inside the network, not outside, right? So inside, so think about it this way. If, outside the network, we have a lot of choices, okay? So for instance, we are carrying this webinar in Zoom, but instead of Zoom, we could have tried, there's dozens other platforms, okay? Some better, some worse, that allow us to carry out this webinar. But once we've selected Zoom, okay, we have absolutely no choice in terms of what path our webinar takes to go from Raleigh Durham, where I am, my office, to wherever you are in Turkey, okay, or anywhere in the world, okay? So we have absolutely no choice on how that traffic is routed. And so we would like to change that and introduce choice inside the network. And basically what we came up is, a kind of a virtuous circle, right, that has three components. One is alternatives, right? So you should be able to have alternatives. If you choose an alternative, right, you choose over another, then you should know what happens. So for instance, if you start seeing that, my video is flickering, right? What is the problem? Is it is it Zoom? Is it the access network in my office? Is it the long-haul network that connects Raleigh to Turkey? Or is it the access network at your side, right? If you don't know who is responsible for whatever happening in the network, then you cannot make a choice and vote with your wallet, right? So this is kind of the circle here. And so I'm not gonna get into the details of that, but basically the kind of the marketplace design was driven by these particular principles that you see here. And again, if you're interested in more details in the work that we've done, I can provide the publications if you want to look at more of that. And so to introduce this marketplace, okay, and I understand this is a kind of a busy image here, and I'm not going to spend a lot of time on each of these, but there are two important things here. You may have heard about the data plane and control plane in a network, okay? And what we did is we introduced what we call the economy plane, okay? So the marketplace straddles the economy and control plane here. There's a planner, and I'm going to talk about that. And then there's other support services, to complete the picture here, like a payment infrastructure, verification infrastructure, and so on. Again, I'm not going to give all the details, but I'm going to explain how this works. And as I said, we've implemented this. We have a prototype that works, that we demonstrated that it works well. And so just, I'll kind of only give you a broad look of how it works, right? So there's a marketplace. This is where you have, it's the repository for services, okay? There's a service provider on this side, and these are the service providers that actually implement the services that are advertised in the marketplace. There's a user, okay? The user could be a human, just like you go on Travelocity, okay? Or it could be an agent acting on your behalf within the computer, okay? And then there's a planner. And so the orchestration part that I'm going to talk about later on is part of the planner, okay? That's the the algorithmics that go into that is the two other pieces that I'm going to discuss. And so if you look at how this works, a service provider lists services into the marketplace, okay? So it will pay, let's say, an amount of money, will place the service here. This is no different than what happens to the app stores, like the Apple Store or the Google Store and so on, right? So, they pay the stores and advertise their applications, okay? It's something similar. It's not applications here, it's services within a network. Now, when a user wants to find a service, right? So the user says, okay, I'm going to have a webinar that, my CEO will talk to everyone in the organization, and everyone in the organization may be located in different parts of the globe. So I want to set up a good, a good connection that connects the CEO to everyone, right? So the user can do one of two things. As I said, they can either search directly the marketplace if they know how to do that, or they can or they can go to a planner and say, okay, this is what I want to do, can you do that for me? The planner will go to the marketplace, will search, okay, and it will return these services to the user, okay. Once the user has the services, just like Travelocity, it gives you a list of itineraries, okay? Then you take a look at those services and you say, okay, this is the one I'm going to purchase, okay? Then you pay the service provider, right? You pay the airline, okay? And then you get a purchase proof. With the purchase proof, you get, with the airline, you get an electronic ticket, okay? With this infrastructure, what you may get is a token, a hash value that goes into your packets. And so when the service provider sees the token, it knows that it belongs to your traffic, and then it will provision in this infrastructure to provide the particular service that your packets are entitled to because you've purchased that particular service. Okay. So that's kind of the idea here. And as I said, we have a prototype that does all this. So now what I want to do is actually go into some detail on the algorithmics of how to do it, okay? You may not realize it, but there is a lot of intelligence behind sites like Travelocity and Expedia, how they collect all the information, how they, what kind of algorithms they use to find those itineraries for you and all that, okay? I'm not going to talk about airlines. I'm going to talk about how we can do that within the network. Okay. So the first thing I'm going to talk about is what is called the shortest path tour problem. Okay. So it's by the way, it's called service chain routing because, as I said before, the traffic has to take a path that that will visit the particular nodes where certain services are provided, right? So you basically chain those services together, and so that's where the term service chain routing comes from. So let me talk about the shortest path tour problem first, and then a special case of that. All right, so this is kind of the Nfv model, right? In the marketplace, you can think of the marketplace as that's where all the services are advertised, right? And so what I'm going to have here, the different colors represents different services. So you may have a VNFA, okay, let's say VNFA is deep packet inspection, okay. That may be offered by multiple providers at different locations. So VNFA from provider 1 at location 1, VNFA from provider 2 at location 4, and so on, right? And then there may be a VNFB, okay, VNFB may be something, a very different service, also from provider 1 at some location, and also from provider 2 from a different location, and so on. And then the VNFC and so on and so forth. Okay, so you have all these services that are advertised. And so from the point of view of the NFV graph, right? So now you can construct a graph and say, okay, provider 1, okay, has 3 services, VNFA, B, and C in these 3 locations in the network, right? And here are the links that connect those different nodes to each other. And the same thing for provider 2, the same thing for provider 3. And actually, this is not as, this picture is not as general as we have done it, because in our work, we actually allow links to go from one provider to another. So perhaps you could go VNFA from provider 1 and then take VNFB from provider 2. Just like, when you're going from one place to another, the first leg may be on JetBlue and the second leg may be on a very different airline. Okay. So now, so this is kind of the model that we have, right? And so here's a couple of interesting observations here. The topology that you see here, okay, it's not the physical topology. It's the virtual, it's kind of the superset of the virtual topologies that I showed you earlier. Why? Because each provider has a virtual node somewhere on the network, right? And in fact, these VNFA nodes could be the same, or it could be different, okay? But each provider has a different virtual network. And so when you put this graph together, the topology is a superset of those VM topologies. And also the nodes and edges that you see here do not represent physical entities. They represent virtual entities. And so a particular link may be served by multiple providers. So let's say I have a 10 gigabit link, which 10 providers share, each at 1 gigabit per second, right? So now each link is 10 links in this topology, okay? So that means now that you may have multiple virtual nodes on a single physical node, and you may have multiple parallel edges, right? And what that means is that you're going to have very large graphs, and therefore, the important thing here is that you need scalable algorithms. You don't just need an algorithm to take you from place A to place B, using the service in between. The reason is, if you go to Travelocity and Expedia, it may take a few seconds for them to start showing you the itineraries. And that is fine. A few seconds is fine. But if you were to wait for minutes, then the benefit of the service would diminish. I mean, you wouldn't do that online, right? So we want scalable algorithms. Okay. So how does that work, right? So the first thing that we looked at is online service chain routing. We are interested in online, right? Online means a customer comes in and says, I'm gonna go from place A to place B with these services in between, right? Find me a path that fulfills certain requirements. So the first thing is, I'm going to look at the easiest problem, which is the shortest path problem. So here's kind of the definition, right? We have a graph, and this is, as I said, the superset of virtual topologies. I have a source S and a destination D. And then I have K non-empty ordered node sets, S1, S2, etc., such that these are subsets of the nodes here. And S1 is where service 1 is offered, and it may be offered at different places in the network. S2 is where service 2 is offered, etc. And SK is where service K is offered. So what I want to find is not a path, and I'm going to explain that in a moment, not a path, but a tour from S to D that visits one node NI within each of these sets, right? And the idea is that your traffic needs to go through service 1 first, then through service 2, etc., all the way up to service K. So this is an ordered set. You can't have the traffic go to SK first and then to S1. It's an ordered set. You have to go in this particular order, S1, S2, etc. So you want to visit one node from S1, then a node from S2, then a node from S3, etc., and then finally a node to SK, then go to your destination. And because of that requirements, and because we don't pose any restrictions on the composition of these sets, right? Your path from the source to the destination may actually visit a node twice, or more than twice. Okay, and that's why it's not a path anymore; it is a tour. Okay. So what we're going to do is minimize the tour cost. That's the simplest problem. Okay. So this is called the shortest path tour problem, or SPTP. Okay. And here's an example of that, right? This is a simple network. Okay. And I have two sets of services. Okay, S1 and S2. S1 is the red service, so that is implemented in nodes C, D, and F. And S2 is the blue service, right? And it is implemented in nodes B and E, right? So think of that, as a game, right? So you want to go, you start on the field, and there are places where people have put up flags of different colors. And you're going to start at this point and make it to a destination point, and you need to grab one flag of the same color, or one flag from each color, but in a particular order. So let's say if you only have two flags, a red and a blue flag, you have to make it from the start to the end in the shortest amounts of time by going first to a place where you can get a red flag, and then go to a place where you get a blue flag, then go to your ends. Okay. So this is exactly the way that we're going to do that. And so in this particular case, A is the source and G is the destination. And here's an example of how one could solve the SPTP problem. Okay. A very simple way to do that is run Dijkstra's algorithm K plus 1 times. So Dijkstra's algorithm is, the basic algorithm that finds shortest paths in a network. So in the first case, you run Dijkstra's algorithm to go from A to any of the nodes that offer the red service. Okay. And then once you are there, you kind of abstract that as a new node, the dummy node S here, and you run Dijkstra's algorithm to go from this node to any of the nodes that offer the blue service. Okay. Then you abstract that as another dummy node S prime, and you find a best path to go from there to the destination. Okay. And at the end, for this particular network with these costs that I have put in there, you can see that the best path is to go from A to C, to D, to E, to G, right? And so that way, in this particular case, it turns out to be a path, not a tour, because you don't visit any node twice, but in general, it will be a tour. Okay. Now, here's the thing. When we looked at this problem, okay, we actually found out this is not our problem. The SPTP has been a problem that was studied back in the 70s, okay? And there's different ways can classify those algorithms, okay? Path to decomposition basically applies Dijkstra's algorithm in different ways. And so there's a single shortest path, or all pair shortest path, or multiple pair shortest path, okay? Again, I'm not gonna go into the details of all of this, but basically these are running Dijkstra's algorithm with small variants. But there are crucial variants. Why? Because some of them were developed for large sparse networks, and others were developed for small dense networks. And so we will see that each one of them has an application for a specific type of network, and so the running times can be very different. Okay. Then there is a layered graph model, which basically constructs a layered graph like the one that I showed you before with the different providers, right? So provider A, provider B, provider B. and that's a layered graph. Then you run a Dijkstra's algorithm of the overall layered graph. And then what we did is we actually came up with a new algorithm, which is we call the depth first tour search. This is our algorithm. And our algorithm differs from, it's basically an extension of Dijkstra's algorithm. And I don't know if you know how familiar with Dijkstra's algorithm, but basically Dijkstra's algorithm in its more efficient version uses a heap, okay? In our case, we don't use just one heap, we use K heaps because we have to go through K segments, okay? And so our algorithm basically tries to do everything in one step rather than going from one node to another node with the first service, then to another node with the second service. It tries to do, you know, go from source to destination in one step, but then keep multiple multiple heaps that make it a very efficient implementation. So let me show you some results of how this works. And by the way, all these algorithms are polynomial, right? So this is a polynomially solved problem. It's not intractable, okay? But nevertheless, as I'm gonna show you, you know, the algorithm that you are gonna use makes a huge difference, okay? So let me show you this. So to characterize topology, right? So we ran a lot of simulation experiments and we varied the number of nodes n, the average nodal degree delta that tells you, you know, how sparse or dense your network is, right? So the larger the delta, the more dense that your network is. K is the number of service sets, right? So how many services your traffic has to go through. And then M is the number of services within each set. In other words, the number of alternative services, right? So service 1 may be offered in 5 different places, okay? And service 2 may be offered in 4 different places. So all these parameters are to characterize the topology. And so here's some results, right? And so these are the kind of the first results, and we were, you know, we did not expect, let put this way, we did not expect this, okay? So what we did is we implemented, or not me basically, but my student implemented 7 different algorithms, okay? That all come from this set. So we implemented each and every of these, and for some of these, we implemented a couple of different versions depending on what was in the literature. So all of these were implemented by my students. So you know, so they use the same language, same programmer, so that you know, that does not account for the difference that you see there. So here's what happens here. These algorithms on the left, as you can see, and by the way, here the algorithm, the graph show you the time it takes for an algorithm versus the number of nodes for this parameters over here, right? So as you can see here, n can be up to 5,000 nodes, right? And remember, we don't really have networks with 5,000 nodes, even wide area networks. But the point here is that we are using virtual networks, right? So we have multiple edges, multiple nodes, and so on. So the network, the virtual networks can be very large, although the physical networks, you know, are much smaller. So what you can see here is that, first of all, these algorithms, these 4 algorithms on the left, they take just a couple of seconds, even for 5,000 nodes. On the other hand, if you look at the algorithms over here, they may take thousands of seconds, right? So we're talking about 3 orders of magnitude difference depending on the algorithm. So one has to be very careful on how to implement the algorithms for large networks. And so some of these algorithms that you see over here, okay, were not meant for very large networks. They perform really well in small settings, okay, but then they cannot scale. And then from all these algorithms here on the left-hand side, again, we can see that there can be an order of magnitude or so between the two that are very efficient and the other two, okay? And in particular, this one, the layer graph, does not really scale. It becomes really computational intensive as n grows. So for the next one, what I'm going to do is I'm only going to concentrate on these two algorithms here, okay? And these algorithms are one version, our own version of the single source shortest path, okay? And our own algorithm, which is shown here in red, okay? And so if you look at these two algorithms only, okay, here's what happens. And this is kind of the interesting thing, is that even for very large numbers of nodes, 5,000 nodes, and large values of delta and m and number of sets and so on, these algorithms take about a second or less to come up with a solution, okay? And that's the important thing, is that you want an algorithm that runs really efficiently on very large networks. And so we have, we have algorithms that can do that. So, basically, what I'm saying is that we're proposing is very feasible for an online setting, okay, where you don't want to wait for a long time. And so the other thing I want to say is that although the red here is our own algorithm, DFTS, the green one, although it is based on a concept that was developed before, it is also our own variants, okay? And so if the original algorithm as it was proposed does not scale very well, but we were able to make improvements to that so that it will bring its running time down, okay, from the blue to the green here, okay? So we had contributions in two areas, not only just a new algorithm, but also an improvement of an existing algorithm, okay? Now, having said that, let me make the problem a little bit more complex, okay? Not only do we want to find a good path, but we also want to minimize congestion, right? So as we route traffic through the network, we are bound to cause congestion. So what we want to be able to do is minimize this congestion, okay? So it's the same problem as before, okay? The only thing that changes is the objective. Before, the objective was the number of the minimum cost. Okay, now I'm going to change that. I'm going to say I want to minimize congestion. So as my primary objective, I want to do load balancing, basically, right? Because that's how you minimize congestion. You minimize congestion by doing load balancing. Once I achieve load balancing, the secondary objective is to minimize the number of hops, because I can do load balancing by sending my traffic to go through a circuitous path around the network, right? But then that will increase delay and so on. So I want to have both goals, right? Load balancing and small number of hops. And so what we're going to do is minimize congestion first, and then see if we can also minimize the number of hops. All right, so what is the wish list for our algorithm? First of all, we would like it to be competitive. Competitive means that has a bounded competitive ratio compared to the optimal solution of the offline algorithm, right? So, in theoretical computer science, in an online algorithm, you run the algorithm for every request that comes in real time, right? Without knowing the future requests, okay? But what happens if you already knew their future requests? If you knew their future requests, then you would be able to run the algorithm offline to find the best routing for all of these requests together, okay? And so, ideally, your online algorithm would have a good competitive ratio compared to the offline algorithm that knows the future, okay? And since we already have an SPTP algorithm that works well, I would like to use that. And how can I use that? I would like to use it by defining an appropriate edge cost function, okay? And in fact, we were able to do both here. And so here's the penalty function that we use, okay? Once after we route a request I, right? So it's an online algorithm, so I have request path coming 1, 2, 3, etc. Right now I'm in the ith request, and so if I route this request on an edge E that has loads Li of V and capacity C of V, then this is the penalty that I'm going to assign to that edge. Okay, let me explain this. Gamma is a constant, okay, that is greater than 1. And that's all you need to know for the time being. It's just a constant, okay. Li over Ci, right? Li is the load of the edge. Le and Ce. Le is the load and Ce is the capacity. So L over C here gives you the congestion of that link, right? So the congestion is 50% or 60% of the capacity, okay. L star is the optimal congestion over in the whole network, okay. So basically what happens here is that as congestion goes up relative to the optimal congestion, your penalty becomes exponentially larger, right? That's the idea here, okay. And then for all the network edges, all you do is you just sum up, the penalty for each edge, basically, okay. Now here's the important thing and why I put this L star in red here. I put it in L star in red because we don't know that quantity, right? It's the optimal congestion. We don't know what the optimal congestion is. Then the question is, okay, but how do I use that if I don't know what L star is? And I'm going to explain that in a moment, okay? And so the key step here is that once I route request I, okay, I increase the penalties function by, it's very simple. I take the shortest path tool that I use to route I, and for these edges E on that tool W, right? Their penalty went up by the traffic of that request. So traffic I here is the traffic on edge E of the shortest path tour, right? And so since I put additional traffic on that edge, its penalty function went up. Okay, so that's really what I'm using as the length function when I'm routing this. Okay, so here's the online algorithm, okay? So to route request I find, remember, I don't know L star. So what I do is I get a lambda value that is an estimate of lambda star, right? I use this lambda instead of lambda star in the penalty function that I showed you before, okay? And I compute the shortest path tour for this particular request. Now, if an edge of the tour has congestion greater than lambda, that means my estimate was low. So what I do is I double the value of lambda and repeat, okay? And because I'm doubling the value of lambda, I close the gap between lambda and the actual value of L star very quickly, okay? So I'm not gonna do this a lot of times, okay? I only have to do that. This is like a binary search in a sense, so it's logarithmic time, okay? And the main result, which I can point you to the paper, the main, and this paper actually, this work has been published recently in the IEEE Transactional Networking, okay? And so these results are from that paper, is that the online algorithm has a competitive ratio of log E, okay? E is the number of edges, which is asymptotically optimal for congestion minimization. In other words, while you may think that log E is a large value because E itself is a large value, we cannot do better, okay? It's a result that says no other algorithm can do better in terms of competitive ratio, okay? And in fact, as I'm gonna show you in the next couple of slides, although the competitive ratio here seems to be very large, right? Logarithmic to, or in the order of the number of edges, the actual, in practice, it's actually very close to optimal. So let me show you this. sorry. Yeah, so before I go to that, so that was the first objective, right? The first objective was minimize congestion. But what happens with hop length, right? We don't want to take a very long path. So here's an example. Suppose now that I have two options to go, from the source here on the left to the destination here on the right. I have two options, right? I have a long path that has a length of 4, but has a small cost. And then if you have a short path, okay, that has a larger cost, in this particular case, a cost of 5, whereas, for instance, here, the cost will be less than 5, okay? So how can I, and so the cost here is a bit smaller than the cost of the short hop path, okay? But I'm forced to take the long path, okay, because I only consider congestion minimization, and so I have to take the longer path, right? So the point here is that what I can do is I can add a small constant to each cost that I computed with a penalty function before. And if I do that, this will favor short paths, okay? And so whenever the difference between the actual cost of a long path and the cost of a short path is relatively small, by adding this constant term, I will favor the shorter path, right? And that way I can tilt, I can incur a bit more congestion, right? But then my traffic will take fewer hops, okay? So let's see how this works. So to evaluate this, we evaluate 4 different algorithms, okay? 3 are baseline algorithms, and then the last one is this competitive online, is our algorithm. The first algorithm is LP offline. Remember, I said that if I have if I know all the requests in advance, then I can set up an integer linear program, solve that, okay, and give me the optimal congestion. Unfortunately, for very large networks, I can't solve the ILP. But what I can do is I can relax it and solve the the corresponding linear program offline. That will give me not the optimal max congestion, but will give me a lower bound of max congestion. Okay. A fewest hops algorithm is where I just use the SPTP algorithm I described earlier with edge length 1. That will give me the shortest hops. I can't do any better than that. Okay. And SPTP online is a simple heuristic that uses the SPTP with the load-dependent edge length. Okay, it's load-dependent, and so that will try to take into account congestion, okay, but not as well as our competitive online algorithm. Okay, so let's compare these algorithms and see what happens. So what I'm showing you here is the first graph is on maximal congestion, and then I'm showing you here the length of the service chain. In other words, how many services traffic requires. And so the first thing that we see that, as we go from 2 to 3 to 4 to 5 to 6 services in the service chain, the load goes up. Okay, and that makes sense because if you need the more services that you need, the longer the path you will take to take you to those different services, and therefore the more that you're going to load the network. Okay. So let's see what these, the different algorithms do. The LP offline algorithm, that's the white bars here, that's the lower bound on congestion. So you can do better than this, okay? The black bars here are the simple heuristic. And so you can see that this is clearly higher than the lower bound. Our algorithm is the competitive online, the gray bar here. And as you can see, we do better than the simple heuristic, okay? But of course, we are above the lower bound, okay? Now, we don't know where the optimal is. So the optimal is somewhere between the top of the white bar and the top of the gray bar. So the optimal is somewhere in between, but unfortunately, we don't know how far it is. But as you can see here, we are not that far away. So although the competitive ratio is log E, as you can see here, the difference is relatively small. Okay. Now, what price do we pay for this in terms of number of COPs? Okay, so in terms of number of COPs, here's the thing. Okay, this is the fewest COP algorithm, right? That uses SPTP with edge cost of 1, so that gives us the lower, the shortest paths. Period. We can't do any better than that. The SPTP online is higher than that, and our algorithm is higher than that, is even more. Okay, so basically, what we are showing here is that compared to the heuristic, we do better in terms of congestion, and the penalty that we pay is about half a hop. Okay, so on average, our traffic will take half, and that does not really change as you go from 2 to 3 to 4 to 5 to 6 services. It's generally just half a hop more. So, and that makes sense. Basically, our algorithm finds better paths because it can use longer paths. But on average, the cost is only half a hop higher, to get the better congestion, the lower congestion. So that kind of concludes my talk, and I think we have a few more minutes, for any questions that you may have. And again, if you are interested in this, I can point you to the papers that we have published.
Thank you, Professor Rouskas. While I was looking at some papers, I saw that usually on virtual networking area, the open challenging problems can be listed as interoperability, resource and service modeling, network service lifetime, and etc. But when compared with your presentation, I have a few questions in mind. The first one is, while making this modeling, especially on the resource and service modeling perspective, did you take into account this different type of service characteristics, or you just assumed all the services are equal?
Right. So in this case, the different services can certainly have different service characteristics, right? Now, for the same service, so we assume that if you have multiple, you have one service that offered by multiple providers, that they're kind of equivalent. In other words, there can be whether you take the service from provider A or provider B, that's equivalent, and so that allows you the flexibility to choose multiple paths. Now, it may be possible, of course, that there may be slight differences between the services, right? And so in this case, it may be possible to kind of adjust the algorithm to take that into account. But this particular work does not do that. Okay, so it assumes that the same service offered by different providers is basically equivalent to each other.
Okay, thank you. The second one is, did you take into account the security issues as far as I can see, because there is no security issues in this model? How this model could change if you take into account the security considerations or security issues?
Right, and so security issues is a kind of a very generic term. Are there any particular security issues that you have in mind? So, for instance,
especially packet inspection, for example.
Right, and so again, one of the services could be, deep packet inspection, right? And so you may want to look for signatures of malicious attacks and so on, right? And so in this particular model, we assume, that if one of the services is a deep packet inspection, they will perform that particular security service for you, right? One of the things that we could easily incorporate in our model is you can say that, look, I really do not care to use services by provider X because I don't trust provider X, okay? And then just like, the airline analogy where you can say, which airlines are you, do you want to include, right? And say, I don't want to include Iranian airlines, right? Because I'm in the US and I either I have security reasons or because my company will not reimburse me if I use an Iranian airline and all that, right? And so I could do that. That is something that we can certainly, that's an additional constraint that we can put in the algorithm to avoid services from provider X, okay? So this type of security. Now, there may be other issues that, we haven't thought about, but generally speaking, the algorithm is relatively simple, that we could kind of enhance it to take other considerations into account.
One more question about how can we relate this study with distributed ledger technologies? Is it possible to include those technologies inside this modeling?
Distributed ledger, that's a good question. I have to say that I haven't, that's actually kind of an intriguing idea that you're mentioning it, but this is not something that I actually have thought about at this point. So I can't really say how this might be used with distributed ledgers. But that's a good point. Something that may have to think about.
Okay, thank you very much. That's all. There are a few more questions, but we are up to our time, so I don't want to spend a lot more time from your time. But if you have time, one more question would be about the performance metric, especially while we are talking about virtual network environments. How about especially on graphical intensive cases like online gaming and those kinds of things? Will that change your modeling?
Online gaming. So no, I think this particular work kind of is kind of agnostic in terms of the services, right? And so online gaming traffic may require certain services that that can be represented, as part of our model here, the Nfv graph. And so and in particular, online gaming might be an example of traffic that would be sensitive to the number of hops, right? So we take that into account, for instance, and it's also sensitive to congestion. So I think, the work that we've been doing, I think would be well applicable to this type of traffic.
Do we need to look at the problem from the quality of experience, not quality of service quality? Because in the online gaming, quality of experience becomes much more important than quality of service. So would that be a problem from this model, from the perspective of this model?
Right. Okay. So in this particular case, you are right. We are taking into account congestion, right? In our model, we use congestion. Okay. Now, a quality of experience is, it depends on, and I'm not, very familiar because I haven't worked on quality of experience, but as long as one can relate quality of experience to properties of the network, then we could apply that, right? So, I don't think we can say, okay, quality of experience is X at the user and then use that to run our algorithm. But if we can say quality of experience X for the user means congestion no more than Y in the network, then we can apply that. Does that make sense?
Yes. Okay, thank you very much for accepting our invitation and giving this very important and new topic presentation on this topic. I just found your paper already.
Okay.
I started reading it beforehand. And it's interesting. I hope from this far we can just elaborate some corporations from the research perspective. Hope to see you in Istanbul after this pandemic.
After the pandemic,
thank you very much once more
absolutely.
for accepting our invitation.
Okay, thank you, Halim. I appreciate it. It was my pleasure, and I hope to see you again, not just virtually. Okay.
Yes, hope to see you in Istanbul Commerce University and
Okay,
see Istanbul together.